6 is piecewise functions. I mentioned this before when we were talking about the absolute value function. The absolute value function is made up of 2 lines. So that's a piecewise function. Is it always 2? No. So a piecewise function is a function defined by using 2 or more rules. So there doesn't 2 or more, so it doesn't have to be just 2 pieces of 2 or more intervals, right? So or more. As a result, the graph is made up of 2 or more pieces of similar or different functions. It doesn't have to be 2 lines. It can be a line with a parabola. It can be a line with a reciprocal function with a square root function. They don't have to be the same. It can be different ones. It can be the same ones. It doesn't have to be just 2. It can be more than 2, right? So 2 or more and similar or different functions. And there's different intervals. So that's a piecewise function, right? So it kind of makes sense. So we're going to do some graphing, just review. First ones are kind of easy, and then we're going to do a little bit more challenging one, and then we'll go backwards. So then I'm going to give you the graph, and you're going to write the equation. So it's like what we did before, but I'm now combining the different graphs. So this first one here, you don't have to number it, but I'm just going to pull it aside. So if I pull it aside, I want to number it. So I know the first one is x squared, so I know that that's just a parabola. The second one is y equals 2x plus 3, which is just a linear. So again, we reviewed this enough so that we should know these things already. So this one here, I know m is 2, and that's 2 over 1, which is the rise over run, right? And this is b is 3, which we know is the y-intercept. Now, I'm going to work in pencil and then show you how I would erase. If you get a little bit more comfortable with this, then you don't have to do as much erasing, right? But for the first little while, I'm going to just show you how I would do it. The first one, I would say, okay, I'm going to graph the x squared. I'm going to graph the x squared. So we got this here. So over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 1, over 1 up 3. So just quick, just because I know how to graph the basic parabola. Started with an easy one. So I would do this. Now, before I do that, I want to check my domain, right? So the interval here. So it's going to be x is less than 2. Less than 2 means it's open dot. So open there. So open. So we know open. We don't have to write this. It's just for my brain, right? Open dot there. And then I know this other one is going to be closed. So this one here, that one will be closed. Okay, so closed and open, so just looking at that. So less than 2 means I want an open dot here at 2. So where I drew that dot there, I'm going to now make that an open dot. Now, what I want you to do is I want you to erase it so that you can make it a distinctly open circle. If it looks like this, like it can't look like this, where you have a dot and this, because I can't tell, is that open or closed? If you have an open dot and a closed dot on the same value, so I don't want that. If it's open and closed, I just want it to be closed. Don't circle it and put a dot there because I can't tell, because see how the dashed lines are there? I can't tell if that dot's supposed to be there or if you were trying to show me it's open. So make it distinct. If it's open, I'm just going to show you an open circle. So I erased it, right? No dot in the middle, and I'm just going to do this. Okay? Doesn't have to be ginormous, but just make it so I can see. Right? So again, just about accuracy, not neatness, but like just make sure I can see it's open. And then if I do happen to have it open on top of a closed, so if I have it open sitting on top of a closed, it just closes it. So if I have an open, but I have a closed one there, just fill it. Don't do this circle thing because it's kind of like, what do you want that to be? Open, closed? I'm not sure. So just an open on top of a closed fills the hole. Okay, so just fills it. That is distinctly open, period. Okay, so I want to be able to look at it and go, yep, that's good. I'm going left because it's less than. So I'm going to take these, I'm going to highlight these and say yes, make sure I can see these values, and then I'm going to go and try to make it neat. Like that. Okay, so it's open, there, done. So make sure it's neat enough so I can read it. I want to be able to just look at the graph, go, yep. If I have to look at it and go, ooh, is that, I can't tell, then that probably means you're missing a half mark somewhere, right? So if I have to stop, pause, and figure out, that's not what we want. So, yep, open there, and less than, so it's open. Okay, this one here is the line. So there's going to be some overlap. Now look here, f of x, g of x, all of those notations mean it's a function. If it's a function, it should pass the vertical line test. There should not be overlapping lines. You know right away you're wrong if you have overlapping lines on your function. You'd be like, whoop, doesn't pass the vertical line test. So if I was drawing this, I know it starts at 3. Not starts at 3, but the y-intercept is at 3. It has a slope of 2, so it does this. Oh, and I should have erased that extra dot if I wasn't using it, but now I'm using it for this one. Now, go there. Now, there should not be overlap, right? So I shouldn't draw the line here because I know, that doesn't work, right? So where is it telling me that? Here, greater than or equal to 2. So then at the 2, I want greater than or equal, so I want this point here to be a solid for sure dot. So greater than or equal, so solid. Okay, so solid there. And it's greater than, which means I'm heading to the right, which means I want you to go back and make sure you erase the extra dots that I didn't need. So make sure there's nothing extra there, nothing overlapping, perfect. Okay, so do a double check to make sure you didn't leave anything extra, and then you're just going to take your line and go ahead and do a line with an arrow saying it continues on forever. Okay, so that was just me clarifying about it's not again about neatness, it's just kind of be accurate with what you're drawing. Any questions or clarification? Okay, so then we're going to answer the question, is the function continuous or discontinuous? You're going to say it's discontinuous at, and you're always giving the x value for where it's discontinuous. So it's going to be discontinuous at x equals 2. If we ask you to name the type or identify the type of discontinuity, you would say it's a jump discontinuity. Okay? We'll make sure it's clear in the question if it's on an evaluation whether or not we want you to identify the type or just state where the discontinuity is. Okay, so if I say identify the discontinuity, state where it is, you would just say this. But if we say identify the type of discontinuity, if there is one, you would say it's a jump discontinuity. It's jump or, and then these are the words, right? Jump, it's point or removable. Removable means it's like you punched a hole through it. So point or removable. Asymptotic or infinite means there's an asymptote there. Makes clear. Yes, question? Punched a hole through it would be, so they connect, but there's a point missing. Punched a hole. So it's a point discontinuity. It's like you removed the point. So that's why they call it removable or point discontinuity. You're like, oh yeah, that makes sense. It's like you removed a little bit. Yes?
So continuous, isn't it just about the domain?
Yeah.
It's like that function's continuous in its domain, right?
No, it's continuous is, remember the definition is, can I draw the whole thing without lifting up my pencil at all? You're not, I never said.
Okay.
You describe the continuity based on the domain, but it wasn't, does the function exist? You're thinking of, does the function exist on that domain, which is not what continuity is. Continuity is that it continues without any jumps, breaks, gaps, or holes. Okay, so yes, the domain is x as an element of real, but that's not what we're asking. So domain and range are different than continuity. Your answering is what's the domain, right? So different. Okay, good. Anything else to clarify? Try it again. Let's do another easy one. So again, you don't have to number it, but if you pull it aside, I'm just showing you that 1 is the reciprocal and 2 is just a linear. Okay, and again, you don't have to do that. You can go right ahead and graph it. Whenever it's a little bit of an easier graph, you can just go right ahead. You don't have to do a T-chart with the points. Go right ahead and graph it. Again, I'm going to start with a pencil, and I'm going to erase the parts that I don't need. So if this is the regular one, I know it's here, 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 and then here, here, and here. Right? At 1/2, it's 2. At 1, it's 1. At 2, it's 1/2. -1. -1, -1/2 is -2, etc. Those 2 points, those 6 points we usually do. Okay, then we have our asymptotes. Now, I want to graph this greater than or equal to -1. So look at this, greater than or equal to -1, so always check that. That would be -1 is here, right? So that point there, that would be my starting point here, so solid dot. So solid dot. Right, solid dot there, greater than or equal, so solid dot at -1, and I'm heading to the right. So I'm going to go this way, and then here. And then just make sure I can see your points. Right there. Okay, and please erase extra points that shouldn't be there anymore. And yes, every time I have a function that has asymptotes, I do want you to explain that there is an asymptote with a dashed line and the equation. Sometimes we don't write the equation. That's because we want you to figure out what the line equation is, right? So sometimes we just show you the dashed line, and that's because we want you to figure out what the value is yourself, whether it's x equals 0 or y equals 0, etc. Okay, so that's on purpose. There you go. So labeled that. And I want the line. So this line here, I know that the m is 2 and the b is 0. Right? So then that means that it would pass through 0, 0 here. And the slope is 2. So I'd go up 2 over 1, up 2, right? Up 2 over 1, up 2 over 1. And then backwards, that would be back 2 like this. So fill the graph. But I don't need all that, right? Because I don't want the overlap. So it's less than -1. So all I needed was here. And I want that to be open. Does that make sense? I want it to be open. So that would be open there. So just make sure it's erased and open. And then to the left, so that means I'm going to go dot, dot. And then to the left, that arrow. And erase the extra dots. That. Nothing extra happening. Beautiful.
That's an open dot at -1, right?
Yes, open dot. Right, and if you're not sure, I'll do this. There we go. I know, that's why I said those dashed lines are confusing, so don't put a dot inside of there. There you go. And I'll zoom in a little, just so you can see. Okay, and then, of course, it is discontinuous. Okay, is that big enough? Zoomed in enough? Okay, so it's discontinuous at yes. Answer the question. Discontinuous where? Yeah. Equals -1. And why? What type is it? Yep, so it's a jump discontinuity. And? Yes, an infinite. And at x equals 0. Don't ignore the infinite discontinuity. People go, but it's part of the graph. I know, but it came with a discontinuity. Like the 1 over x graph actually has its own discontinuity. So don't forget that one, right? So, and that would be an infinite or asymptotic, right? Infinite discontinuity. Okay, so don't forget that one. Do state both of them. People go, do you want to state the one that's in the graph? Yeah, because it came with the graph, right? So don't forget that there is one originally in the graph.